Electromagnetism is one of the most beautiful and interesting theories in physics. And honestly, it was one of my favorite subjects in school. But for many people, it just feels like a bunch of random equations, something you apply in very specific situations, without really understanding where they come from. And my goal is to change that. I want to show you what these equations actually mean, where they come from, and more importantly, how to actually use them. And to do that, we need to start with the language of electromagnetism. So, let's begin. Some quantities in physics are described completely by a single number. Temperature, density, energy. These quantities don't point anywhere. They simply tell us how much of something there is. We call these quantities scalars. But other quantities behave differently. Sometimes, a number alone isn't enough. Velocity, force, and the electric field also carry direction. And that changes everything. These are vectors. And to remind ourselves that a quantity has direction, we usually draw a small arrow above its symbol, like this. Now, mathematically, a vector in 3 dimensions is written like this. At first, this notation may look abstract, but it's actually describing something very simple. The symbol r represents the real numbers, and the exponent 3 tells us that we need 3 of them. One number for the x direction, one number for the y direction, and one for the z direction. And together, these components describe a vector in 3-dimensional space. And this leads us to one important idea, that a vector is not fundamentally magnitude plus direction as 2 separate ingredients, but instead, that the vector is defined by its components, Vx, Vy, and Vz. And its magnitude and direction are properties that we compute from them. Now, even though the world around us is 3-dimensional, working in full 3D can quickly become difficult to visualize, and also to animate, to be honest. So, throughout this series, we will often simplify things into 2 dimensions. So instead of R3, we will work in R2, a flat 2-dimensional world. The geometry becomes easier to see, even though the underlying ideas remain exactly the same. And before we continue, there's one last distinction we need to make. A point like XYZ is simply a location in space, an address. We usually write it as a position vector. R tells us where we are. But a vector is something that exists at that location, like a temperature value, a force, a velocity, and that distinction between the location and the object living there is going to become extremely important once we begin talking about fields. Just a quick pause. This video is sponsored by absolutely no one. But if you'd like to support the channel, consider subscribing and giving this video a thumbs up. So, back to the video. And now, imagine this. What if every single point in space had its own value, whether it's a scalar or a vector? Not just one point, but like every point, all at the same time. To answer that, we need to veil some physical intuition. Now, imagine that you're in a room with the heater on. If you carry a thermometer around the room, every location gives you a different temperature reading. Some regions are warmer and others are colder. And that invisible distribution of values throughout space is what we call a field. More specifically, a scalar field. And mathematically, we write it like this. And this notation simply means that the field takes a position in 3-dimensional space and assigns a real number to it. In this case, temperature. But some fields carry more information than that. Imagine a flowing river. At every point, the water has not only a speed, but also a direction. Some regions flow faster, others curve around rocks and obstacles. Now, every point in space is associated with a vector. That is a vector field. And mathematically, we write it like this, which means that the input is still a position vector in 3-dimensional space. But now, instead of returning a single number, the field returns an entire vector. And like I mentioned earlier, to make these ideas easier to visualize, we'll often simplify things into 2 dimensions. So the same ideas become this. And even though the picture is now flat, the underlying idea remains exactly the same. You give the scalar field a position in R2 and it gives you back a real number, a scalar. But if you give a vector field a position in R2, it gives you back a vector. But now that we're looking at these fields, another important question appears. How do we represent strength? Because a field does not only tell us where something points, it also tells us how strong it is, its magnitude. And one way to represent this is through the length of the arrows. Longer arrows represent stronger regions of the field, but in practice, this quickly becomes difficult to read. So instead, we also use color. Cooler colors usually represent weaker regions of the field, while warmer colors represent stronger ones. This allows us to visualize intensity better. Everything we've discussed so far has been mathematics, scalars, vectors, and fields. But in physics, fields are not just abstract objects. They describe something physically real. Instead of thinking that objects act on each other from far away, we describe how they modify the space around them. And that brings us to the electric field. If you place a charge somewhere in space, something changes. The space around that charge is no longer the same. Every nearby point now has an associated direction and strength. That structure, spread throughout space, is what we call the electric field. We represent it mathematically like this. Again, the vector r specifies a position in space, the location where we want to evaluate the field, and E is the value of the electric field at that particular location. So this notation simply means, at the position r, the field assigns a vector E. You give the field a location and it gives you back an arrow, a vector. You might be wondering, in the case of the electric field, what does the arrow actually represent? You can think of it like this. If I place a tiny positive charge at some point in space, how would it move? The electric field answers that question. It tells us the direction that tiny positive charge would be pushed. And the word tiny is important, because if we try to measure the field using a large charge, that charge would create its own electric field, and it would actually modify the field itself that we're trying to measure. But a really tiny infinitesimal test charge is different. It responds to the field without significantly modifying it. So a tiny positive charge moves along the direction of the field. A negative charge, however, moves in the opposite direction. So when you look at the arrows of an electric field, you should think, if I place a tiny infinitesimal positive charge, this is the direction it would move. And that idea will become the foundation for everything that follows. In this chapter, we build the mathematical language behind fields. We introduced the difference between scalars and vectors. We saw how positions in space can be represented using vectors in R3. And we explore how fields assign information to every point in space, whether it's a scalar or a vector. And we also saw why visualizing these fields require more than just arrows alone. Magnitude matters too. And by combining direction with color, we can begin turning these abstract mathematical objects into something we can actually interpret visually. And finally, we introduce our first physical example, the electric field, a structure that assigns a vector to every point around a charge. But this is only the beginning. So far, we have focused on the language. Now we're ready to start using it. In the next chapter, we'll study how electric charges generate these fields, how their strength depends on distance, and how all of this naturally leads to Coulomb's law. Also, thanks to all the Patreon supporters for helping make this video possible. Thank you, and I'll see you in the next one.